Okay, so this last unit that we have before the final focuses, like I said, on sampling distributions. So like we've been talking about, a distribution, any distribution, always gives the possible values and how often they occur. So we've talked about a sample distribution and we've talked about a population distribution. So today is a new one, it's called a sampling distribution. The way this unit is going to work is we're going to talk about sampling distributions in general, and then we're going to focus on proportion and mean, because those are measures that a lot of statistics use. Just so you know, there's nothing new that you're going to learn on the calculator. There's a lot of stuff on the formula sheet, though. So when we get to proportion and mean, we'll look at the formula sheet. Right now, it doesn't really matter to us, though. So if you can go to the first page of notes, if you haven't already, there's some vocabulary that we need to talk about. First thing to talk about is what is the difference between a parameter and a statistic. A parameter is calculated for the population. So in the tank example that we did, when we started with those 100, those numbers 1 to 100, that is a parameter. That 100 is the sample size for, not sample, is the size of the population. So that's a parameter. A statistic, on the other hand, is calculated for a sample. So when those people did 2 times the median rather. So some people did 2 times the median. That was a statistic because it came from a sample. Or if we said we took samples of size 7, that's a statistic. That comes from a sample, not from a population. What's really nice to remember is P goes with P, so parameter, population, S goes with S, so statistic and sample. And how are they related? Well, like we talked about in the activity, statistics estimate parameters. So remember, we often want to know something about the population. Like we want to know how many German tanks are there, but we can't go out and actually find all of them and count them. So we want to estimate something about the population, but we use a statistic instead. There's some that you guys already know. X bar is a statistic. That's a sample mean. That is used to estimate a population mean. Likewise, a sample standard deviation estimates a population standard deviation. And like we've talked about, if I take one sample and find the sample mean, it is likely not going to be exactly the same as the population mean. So taking one sample and calculating that statistic is likely not going to be exactly the same as the population parameter. It's just an estimate. What I need us to know right here is that misusing these terms is a big source of lost credit on the AP exam. So for example, what sometimes people will do is people will say mu is the sample mean blah, blah, blah. You're going to lose credit there. Mu is for a population, not a sample. So that's going to cause you to lose credit. Okay, so let's take a look at the first example. In these examples, we are going to identify the sample, the statistic, the population, and the parameter. A Pew Research Center poll asked 1,102 randomly selected 12 to 17-year-olds in the U.S. if they have a cell phone. Of the respondents, 71% said yes. Okay, sample is who we actually asked. So the sample is the 1,102 randomly selected 12 to 17-year-olds in the U.S. That's who we actually surveyed. The population is who we're interested in. We are interested in all 12 to 17-year-olds in the US. Just a little bit of a throwback. Why does it matter that these 12 to 17-year-olds were randomly selected? Why does it matter that they were randomly selected versus volunteering to take this survey?
No bias.
Yeah, has to do with bias. It allows us to what, Michaela?
Like you can apply it to the whole population, not just like similar.
Okay. Do you remember a random sample allows us to generalize to the population? So whatever conclusion happens here, we can generalize that estimate to the population. Okay, so then the statistic is that 71%. The parameter, well, we don't know the parameter. That's what we're trying to estimate. The parameter, if we were to put it in words, is the population proportion of all 12 to 17-year-olds answering yes to do you have a cell phone? Okay. How confident are you that if we actually talked to every 12 to 17-year-old and asked them if they have a cell phone, how confident are you that 71% of all of them would say yes? Do you think it's going to be exactly 71%? Probably not. Probably not. Just like on all these samples we had on the back board, very rarely did we get exactly 100. We hope it's close, but it's probably not going to be exactly the same. Okay, I want you to take 2 minutes with the person next to you and do part B, please. Please use detail. Do I have any volunteers for any of those 4 terms? If not, I'll just call on a few people. Thank you, I appreciate it.
Sample of 50 patients.
Great, so the sample, not a whole lot there, it's just the 50 patients. Adam, what is the population then? All 10-year-old boys. Okay, great. Jessica, can you tell me either the statistic or the parameter? Okay, so statistic is that Q3, which is 56. And then Sophie, finish it out. What is the parameter?
The population portion of all 10-year-old boys.
So the population part, I agree with. If we go back to the measurement that was taken, if we took this same measurement but for the whole population, what is this? Q3? What is that in words? I don't remember.
The top, or like the 75th percentile.
The 75th percentile, sometimes called the upper quartile. So it's the population upper quartile, or Q3, for all 10-year-old boys. So if we go back to the previous example, the reason this was proportion is because 71% is a proportion, expressed as a percent, but same idea. Okay, so this leads us to a very, very important term, which is sampling variability. And we've talked about this term actually already. This term means that different samples from the same population will give different values for a statistic. And we saw that in the dot plot on the back. We all were looking at the same population, 1 to 100, We were all taking samples of the same size. In the 2 times the median group, almost every time people got different answers. Occasionally, 2 times the median was the same. Similar idea in the next one, mean plus 3 standard deviations. Same population, same statistic, but gave us different values. So that is this idea of sampling variability. So the question, of course, why do we care? We want to estimate that sampling variability. Like we talked about back here, we want that sampling variability to be small. So we want to estimate the sampling variability. So that we know how close our estimate are to the truth. So we're only going to take one sample, and we want to be able to estimate how far away do we think that sample estimate is from the truth. And how far away that is, that's called the margin of error. So what we can do with statistics is we can estimate that margin of error. We're not going to do that with this unit, but that's where we're going to eventually. Okay, so this leads us to a sampling distribution. I cannot stress enough that the term distribution always means the same thing. Students in stats tend to get confused because there's 3 different distributions, but the term distribution always means the same thing. Distribution always shows the possible values and how likely they are to occur. So far, we know a sample distribution, and we know a population distribution. Distribution is also often displayed in a table or a graph. So we happened to put all of our values on a dot plot, but we could have done the same thing with a graph. Okay, so now we are looking at the distribution of a statistic. So like we talked about, each dot represents an entire sample and the statistic for that one sample. So again, the question of why do we care? We need to know how likely various values are. Where this is going to lead us to is that question that many of us don't like: do we have convincing evidence? Okay, so the last thing that we are going to do in our notes is on the next page. We are going to look at 2 different sampling distributions. We are going to make them. Are there any questions for me before we try our hand at actually making a sampling distribution? Okay, so here is the example. A father has 4 children with ages of 12, 15, 16, and 19. Determine the sampling distribution of the sample mean age x bar and the sampling distribution of the sample range of ages for samples of size n equals 2. Okay, first thing that you're always going to do, if it's talking about a sampling distribution, we need to look at all samples of the same size. So we are looking at all samples of size 2. So that's the first thing that I'm going to do, is I'm going to write out all those samples of size 2. And I'm going to do this on a table because I'm going to need to write some other things down. So I could choose the 12 and the 15-year-old, or the 12 and the 16-year-old, or the 12 and the 19-year-old. I could choose the 15 and 16-year-old, the 15 and 19-year-old, or the 16 and 19-year-old. Those are all the possible samples. That's it. So the sampling distribution is going to show the distribution, all the possible values of a statistic and how likely they are to occur. If we look at X bar first, so what I'm going to do for each of these samples is I'm going to calculate the sample mean X bar. And those values are 13.5, 14, 15.5, 15.5, 17, and 17.5. So if I want to display that distribution then, I have to go from 13 to 17.5. So 13, 14, 15, 16, 17, 18. So each dot is going to represent a sample mean. So I have 13.5, I have 14, I have 15.5, 15.5, 17, and 17.5. So this is a sampling distribution. All the possible values of X bar and how often they occur. Now, we use X bar to estimate what? What does X bar estimate? Population mean. So it might be interesting for you to know the population mean is 15.5. So if we look at our dot plot, 15.5 right there. So do you think that X bar is a good estimate of mu, knowing that the true value is 15.5? Yeah, why? Center, right? So if we took all of those X bars and we averaged them off, we would also get 15.5. Okay, so what that tells us is X bar is, like we said, an unbiased estimate of mu. In practical terms, it's a pretty good estimator of mu. Now, if we take one sample, we're not necessarily going to get that 15.5, but in the long run, we're going to average out at 15.5. We've got one more to do. We are also asked for the sampling distribution of sample range. So if we do that, for each of these samples, now we're going to calculate range. How do you calculate range? Max minus min. We only have two numbers, right? So all you're doing is subtracting those two numbers. So we get 3, 4, 7, 1, 4, 3. So if we graph those now, so we have 1, 2, 3, 4, 5, 6, 7. So this is 3, 4, 7, 1, 4, 3. Okay, what is the actual range of the population? Actual range of the population? 7. So that's right here. So the population range, there's no symbol for that, is 7. Do we think then that our sample range is a good estimate? No, because the center's not at 7. if you actually found the center of all of those ranges, so if you actually averaged up those 6 ranges, you would get 3.67. So our sample range tends to be too small. Okay, 2 last things I want us to write down. What that tells us is sample range is a biased estimate. In other words, sample range, not very helpful in estimating population range. Okay, the other big thing that I want us to write down. This was a population of size 4. How practical do you think this process is in general? Could I do this with the population of Prospect High School? That's not even a big population. That's only 2,000 people. But still, it would be really hard to do. So what I want us to know is this is often not possible. It's often not possible. So instead what we do is we consider a smaller population just to get the idea.